To see a world in a grain of sand, and a heaven in a wild flower. Hold infinity in the palm of your hand, and eternity in an hour. It's a nice little poem. It's the first 4 lines from Auguries of Innocence by William Blake. Very good poet. I recommend checking out some of his stuff. He's got some really nice poems. It's quite a nice and relevant poem to what I am going to be doing with you now, because what I want to look at is proof by induction. Proof by induction is a really, really cool technique we can use in maths to prove that certain statements are true for all integers by looking at a specific small case. So we look at a small case, we hold infinity in the palm of our hand, and then we expand that to look at the wider case for the infinite of all numbers. So proof by induction, we use it to prove a general statement is true for all integers, and any proof made by this method will consist of 4 steps, which you're going to have to do every single time you do a question on it. So I'm just going to talk through those steps, and I'm going to jump straight in and explain what they mean. It can be a little bit difficult to get your head around this. It's quite a conceptually difficult topic, even if maybe some of the maths is actually not too hard at times. So the first thing we always do in a proof by induction is we show that whatever statement we want to prove is true when n equals 1. So for example, this is my first proof that I'm going to do in a little bit. Prove by induction that for the natural numbers that are positive, integers that are positive, this series is equal to n over n plus 1. So for example, if n was 100 and I added up all the numbers to 100 in this way, would that give me 100 over 101? And that's what we want to prove. So let's just turn off WhatsApp. Let's have a look at this. So that's the first thing we're going to do. We have an assumptive step, an inductive step, and then a conclusion. We're going to combine all these things to come to our conclusion. And I'm not going to explain these in too much detail at this point, because we'll see what they mean by doing them. So if we're going to do a proof by induction, the first thing I always want to do is write out all of my steps one by one and kind of work through it like that. So the basis, the first thing, the basis step, is showing that the statement is true for n equals 1. And this is again something that you actually, it's quite nice because you actually get a mark for doing this every single time you do it. There's lots of easy marks you can get for this topic, even if you get something that's a really difficult piece of algebra. So we're going to show that is this true. If n is 1, then the sum to 1 of 1 over r plus 1, is that equal to 1 over 1 plus 1? i.e. I've just replaced all the n's with 1's. So if I'm doing this from 1 to 1, it's literally just going to be the first term. So I'm doing 1 over 1 times 1 plus 1. Is that equal to 1 over 1 plus 1? And I go half equals a half. So I'm going to say yes, true for n equals 1. So this is your first step. You need to write out something like this, both sides of the equation, show that when you put in your value for 1, n equals 1, then you get the same thing on each side. Then make a little statement, say yes, it's true when n equals 1. So the next step that we're going to do is the assumptive step. So the assumptive step, it's also, it's not very difficult at all. We're just going to say, we'll assume that this is true when n equals k. So we know for certain that this is true when n equals 1. And we're now going to make an assumption. And we're going to assume true for n equals k. So if n equals k, we're going to have our sum. We're going to go from 1, instead of going to n, we're actually going to k here. And we're going to do still 1 over r plus 1, because r is the variable in this series. And we're going to say that is equal to k over k plus 1. So we've assumed that this is true. So we're assuming that there's going to be some value k that exists, that when we do this, we get the right answer. So we get what we want. So like my example is if it's 100, would it still be true? I mean, we could literally just put 100 in here and see if it worked. Now, it would work because we're going to prove that it's true. We're not going to do it with an actual number. We're just going to say, well, let's assume that we've got a value k that exists and that this is going to be true for that value. So those two steps are relatively little easy bits of this. And now we move on to the tricky stuff. And also, actually, this might seem a little bit tricky already because you might be thinking, what the hell am I doing? So what we need to do next is known as the inductive step. So the inductive step is that we show, based on our assumption, that the statement is true for n equals k plus 1. So what I want to do is I want to take this assumption I've made and I want to show that using this assumption the next value would also be correct. So if it was true up to k, based on what my assumed statement I made about k, this should also be true for k plus 1. So what I always do at this point is I do like a little thing called what I want. What I want is I want to manipulate this piece of algebra to give me a statement equivalent to what I have here, but for k plus 1 instead of k, because I want to show that when it's true for k, it's also true for k plus 1. So I want the exact same thing I have here, but in place of all the k's, I actually want k plus 1's instead. So I would obviously normally write k plus 2 here, but I'm going to put k plus 1 to show that this k has become k plus 1. So it would be k plus 1 over k plus 2. So if I algebraically end up with some kind of expression then which is the same as this, then I've done my job. So the way that we always want to do the inductive step is we want to take our statement that we assumed was true. So this r plus 1 equals k over k plus 1, and we're going to add the next term to it, because I can treat this like an equation. For all intents and purposes, remember, this is a true statement. We've assumed it's true. So what I want to do is I always want to think in this kind of question, add the next term. So I want to think, what's the next term for this? So the final term, if I wrote out this series, the first term would be 1 over 1 times 1 plus 1, which I already wrote up at the top here. I'd keep going, increasing my values until I got to k. So the final term in this series would be 1 over k, k plus 1. So what I'm going to do is I'm going to take both sides of my equation that I have here, and I'm going to add that next term onto it. So I've still got this, and I'm adding the next term that would exist after the kth term, and the next term after the kth term would be the k plus 1th term. And I've kind of done exactly what I did earlier, which is instead of simplifying it, I've left the r's as k plus 1's instead to show that that's what I've done. So this is still the same thing. Oops. But I'm adding, because it's an equation, I'm balancing both sides. I'm adding this to both sides. So this bit here, which I've added on both sides, is the next term that I would get if I carried on this series to plus 1. So I've just added it on. What that means is I can now look at this and I can simplify it in a couple of different ways. So the first thing I can do is I can really easily simplify this side, because I can say, well, because I just added the next term on, I can just take this and put it inside and say, well, I did this. Because summing this to the next term would just be putting k plus 1 here. And that is what this term is. So I've kind of collapsed this back inside my series that I had here. And then I'm gonna simplify this now, and we're just going to do a little bit of algebra. It's quite an easy piece of algebra as well, actually. So this is the expression I get here. Now, with this, I've actually done what I wanted to do on the left-hand side already. Because remember I said this is what I want up here at the top right, this thing. Well, I've already got that. By just adding the next term on, I've got it right here. So now all I need to do is simplify what's on the right and hope it turns into something that is equivalent to what's on the right here. So this is quite easy to simplify. We only have to give them a k plus 2 for a common denominator. So we're going to multiply this left-hand fraction by k plus 2. It's not too difficult. And that gives them a common denominator of k plus 1, k plus 2. Bit of simplifying. So sometimes the thing with this is you do get sometimes quite complicated algebraic expressions on this right hand side, and it's a part of the trick of being able to do these questions is knowing whether you should expand it or not. In this case we do have to expand it. I'm going to show you one where we don't in a second. So if I expand this, it gives me k squared plus 2k plus 1 over k plus 1 k plus 2. The top of this is just k plus 1 squared. So let's write this again. And then you can see here, well, this squared and this k plus 1 will cancel each other. And what I'll get is k plus 1 over k plus 2. Which is what I wanted. So if we assume that it's true for n equals k, this implies it's true. Sorry, it implies it's true for n equals k plus 1. Because what I did was I took my assumption, I just did a pretty simple piece of maths to it. I just added the same thing to both sides, which I chose because it's the next thing in this series. If I went to k plus 1, this would have been the last term, and that's what I wanted. I wanted it to be k plus 1, so I added that to both sides, which is a perfectly legal piece of algebra, and then I just simplified what's on the right here. So that does give me something which is exactly what I want, because this is what I want up here. And this is what I recommend you always do. Write out what you want, and then you kind of know what you're aiming towards. And I can see, because we're pretty good at algebra, we can see from here this is pretty quickly going to turn into this, or k plus 1 over k plus 2. So that's the third step done. That's usually the tricky bit. We always want to look at the series and then add the next term on. And then what we want to do is our final step, which is our conclusion. And you must always do the conclusion. It's usually worth a couple of marks. It has to be written correctly. So we have to make a statement. So we're actually going to just rephrase what I wrote up here. So if this is true for n equals k, it implies it's true for n equals k plus 1. And since it is true for n equals 1, it must be true all n. So let me explain that statement. Zoom out a little bit so we can see everything. So this is my proof. What I've said is if I assume that it's true for some random value k, based on this little bit of algebra I've done, it is going to be true for the next k value. So if it's true for k, it is true for k plus 1. And what we could say now is I could say, well, what if k was 1? If k was 1, like it was up here, where it was definitely true, because it's always true for the next value, it would be true for 2. And then it would be true for 3. And then it would be true for 4. And that would carry on going forever. So I would have it proven to be true for every possible value based on these statements. So, I know this is a little bit hard. Give it a little pause and have a little think about it. If you're struggling, send me a message on Teams if you want me to explain any more detail or go over it again. I'm going to jump into the next proof. This is one with a little bit more complicated algebra, and there's a couple of nice tricks you can do with this. So, prove by induction for any positive integer n that this is true. So we're going to always follow the same thing here. Number 1, basis. So if n equals 1, let's put a 1 there. If n equals 1, we're going to have the sum from 1 to 1 of r cubed equals a quarter of 1 times 1 plus 1 squared. So this is just 1 cubed, because it's just the first term of this series. And this is a quarter times 2 squared, which is 4. So we get 1 equals 1. So yeah, this is true for n equals 1. Second thing, assumptive step. So our assumption here, just always going to say, assume it's true for k. So from r equals 1 to k of r cubed so now we just have k squared, k plus 1 squared instead. Number 3, inductive step. So we take the next term of this and we add it on. I'm going to rewrite it just to keep it tidy. So r equals 1, r cubed equals a quarter, k squared, k plus 1 squared. So scroll down a bit because I'm just doing algebra here now. The next term, the k plus 1, because the final term of this is just when k is subbed in, so that's k cubed. So the next term that we're adding on to both sides is going to be k plus 1 cubed. So we're adding that on both sides. And then we can do exactly the same thing that we did before, which is we can just collapse this k plus 1 cubed inside the series and write a k plus 1 at the top instead. So k plus 1 from r equals 1 of r cubed equals this stuff. So this is what I mean by the algebra. A fool's mistake here is to expand this. If you expand this, you're going to have to simplify it again, because remember, what we want to write is what do we want, and what we want this to be is the sum, the same thing but with k plus 1s instead of k's. So we want it to be this on the right hand side, which we do have, and we want it to be a quarter of k plus 1 squared multiplied by k plus 1 plus 1 squared. Because obviously if this became k plus 1, this would be k plus 2. So what we really want it to algebraically simplify to is a quarter k plus 1 squared, k plus 2 squared. So the number one trick when you have brackets like this is to factorize. This has got a common factor in both terms of k plus 1 squared. This and this. So rather than expanding, I want to think, well, I'm going to factorize k plus 1 squared from both of them, which is going to leave me with a quarter of k squared plus k plus 1. Because if I take k plus 1 squared from this, it's just outside, and if I take k plus 1 squared from k plus 1 cubed, it leaves me with k plus 1. And we want to tidy this up yet further, because I don't want this quarter inside. What I actually want is for it to be a quarter k plus 1 squared, as you can see at the top right. So I'm going to factorize the quarter as well, and then that actually does give me what I want there. We just have to be a little bit careful when we do this and make sure we remember our rules for factorizing, but you should be familiar with this kind of factorization. So k plus 1, I've factored a quarter from this. I just need to remember now that if I factor a quarter, I'm factoring from the whole of the squared brackets that I've written. So this would actually become 4k plus 4. Because now I can think, well, what would happen if I multiplied a quarter back into it? I get a quarter k squared, a quarter times 4k, which give me k, and a quarter times 4, which give me 1. So that has given me exactly what I want. And now, so again, an okay piece of algebra from here. This is just k plus 2 squared. And that's exactly what we wanted. That's the same thing that I said I wanted in my original expression. So if we look up here, this bit and this bit is the same thing. So I've done it. So now I just make my statement. I say, all right, conclusion. So therefore, if it is true for n equals k, it's true. I've written this in a slightly different way, but you know, for n equals k plus 1, and then we write, since it's true for n equals 1, must be true for all values of k, or all k. That's right, values of k, but let's make it as neat and sensible. Because if it's true for k, if we assume it's true for k and it's true for k plus 1, then well, if we just say, well, k was 1, then it must be true for 2. And then because it's true for 2, if k is 2, it must be true for 3, blah, 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 blah. It goes on forever. So there we are again. A nice proof. And you'll have seen some of these series in series chapter 3, I think it is, that you've been doing this week. So now we look at proving them using this inductive method. It's very clever. I'm going to leave it there for this video. Give you a little bit of time to work on exercise 8a. You should do all of it. These proofs, there's only a finite number of them they can be. They always have the same sort of tricks in them, like factorizing out the bracket and all that sort of business. So you need to make sure that you are covering all of the possible questions, because they're quite often very similar in the exam. That's going to be it from me. Thank you very much.